Stefany Allaire recently announced that she is working on a lower cost version of the C256 Foenix called the C256 Foenix U, or User Edition. And since that should be, one hopes a higher volume item with more users on it, some of whom may want to figure out 65816 assembly code, I thought this might be a good time to start this project that I had in the back of my mind for a long time, which is a series of tutorial videos about how you do assembly for the 65816 processor. So I've had difficulty figuring out how I want to structure these tutorials. I don't want the videos to be too long and boring, so I think what I'm going to try to do here is to focus the videos around building a larger demo or a simple video game for the Foenix, and for each video focus on those features of the 65816 processor that we'll need to do the particular feature that we're going to add to the game in that video. And hopefully that will show you both why you would want to use some particular feature and and how that works in the CPU, but then also not overload you with details that you don't need right away. This video is going to be a little bit longer, however, because I want to go over the tools and kind of the basics of assembly language and machine language in case people don't know. So let's start to get into it. First off, what are the tools that you're going to need to do assembly language for the Foenix? First of all, you're going to need to have a way to run the code. That should be fairly obvious. You kind of have two choices here. You can use, if you happen to have a Foenix, a physical version of the C256 Foenix itself, you can use that. If you don't have that and you do have a Windows 10 system, there is the Foenix IDE and emulator that is available from GitHub. I'll put a link in the description of the video below. And that emulator provides most of the features of the Foenix and has the 65816 processor emulator built into it that runs pretty well, and you can use that to run test code and so on. In addition, you're going to need to have some way of editing the code, and assembly language is written as ASCII text files. So really anything that you use to write an ASCII text file will work. Two popular ones right now are Visual Studio Code and Atom, both of which are free. But really anything will work. Emacs, VI, Vim, whatever, Notepad+, whatever you like will do. And then finally, you're going to need to have some way of assembling the code. And there are three development packages that I know of for the 65-bit16. One of them is 64 tasks, which is what we have been using for the kernel of the C256 and for the basic implementation. That's the one I kind of recommend for most circumstances. It's got a nice balance of features and so on. It's not perfect, but none of these are. Another assembler is the CA65, which is part of this, I think it's called the CC65 package, the C compiler for the 6502. That's also freely available. And then Western Design Center has its own C compiler and assembly package that you can get. You have to register with their site and so on, but you can get that. So those are kind of the three choices that I know of. I think there are other options as well. I will be using 64 tasks for these tutorials. And I'll put a link to 64 tasks' repository in the description as well. So now let's get into a little bit about the 65-bit16 processor in a general way. And if you already understand this stuff, you feel free to skip ahead and get into the actual tutorial. But in case you've not really encountered the processor at all, I wanted to talk about its architecture in a very basic sense first. So it's a memory and register style processor. You read stuff out of memory, you write stuff to memory, and you have some registers in the CPU that you can use for storage and for various other functions. This is pretty much the case for most of the processors that you'll encounter in the world today. Different processors kind of the way they differ in the assembly language sense is in what registers that they have available and what those registers do. Some CPUs have got a lot of registers that all work pretty much the same way, or have a couple different classes that work in similar ways. Some processors have very few registers, especially the older style processors. The 65816, as a descendant of the 6502, has very few registers. And here I have a little description of the main ones that we're going to be dealing with. You have a program counter, which is abbreviated PC, and that is the address of the instruction that the processor is executing, or is going to be executing depending on the stage that the processor is in at the moment. It's really the pointer into code for execution. The other, another register that you have here is called the accumulator. It's typically designated A, and this is really your workhorse register for the 6502. Math operations, logic operations, that sort of thing, they all work with the accumulator. They may also work with different locations in memory, but for the most part they're working with the accumulator. So that's really the one that you're going to be using the most in terms of doing operations. Then you have two index registers here, X and Y. And these index registers are, as you might expect, indexes into memory. They're kind of like pointers, or you can think of them as like little cursors that are pointing into, for instance, an array. If you wanted to iterate through an array and look at the different values in the array, the index registers can be used as offsets into those elements in the array. They can also be used for just kind of general data storage. You can stick a value into X or into Y and keep it there for the moment, pull it back out, and do certain things with it, but not as much as you can do with the accumulator. Then we have three registers I'm going to kind of skip over here: the stack pointer, the direct page, and data bank registers. In general, these are kind of pointers into special areas of memory. They do things, special things that we're not going to get into in this tutorial, but we will be getting into those soon. And then finally we have what's called the status register, which is abbreviated P. This contains a set of bit flags, 1 or 0, true or false, that indicate either the status of the processor or let you control certain aspects of the processor and what it's going to do. Again, this is something that we're going to get into later, so we're going to kind of skip over this a little bit, although we will touch a status register in this tutorial here. So now I want to get into what is machine language in a general sense and what is assembly language in a general sense, and what do these things look like. Again, if you've done assembly language or machine language on another processor, this is going to be old hat. Feel free to skip ahead in the video. Now, machine language is really just a stream of instructions to the processor, a stream of bytes, really, that the processor understands and knows how to execute. You see here an example of, 6 different bytes. They look pretty obscure. It may not be understandable on first glance, but these are actually 2 machine language instructions for the 65816. The instructions themselves consist of opcodes. There's 1 opcode byte per instruction. It's always the first byte of the instruction. And the opcode is basically telling the processor what function it is to perform for that instruction. Adding 2 numbers, subtracting 2 numbers, doing a logical OR, making a decision, that kind of thing. Included with the instruction is anything from 0 to 3 what are called operand bytes. These operands provide data for the instruction. That could be, if you wanted to add 2 numbers, it might be the number that you want to add to what's in the accumulator. It might be an indication of what address contains the value that you want to add, that sort of thing. And in this particular example, the first instruction has a single byte operand, and the second instruction has a 3-byte operand. And I should note that the the 65816 is a little endian processor, which means that when there's a multi-byte number, so a number of magnitude greater than 256, or greater than 255 rather, it will have multiple bytes, and the bytes will be arranged in least significant byte first. So what we have here is 0700AF. That number is actually AF0007 when you correct for the little endian ordering of numbers. Some processors are big endian, meaning that the most significant byte is written first. But the 65816 writes it the other way around, least significant first. Now, machine language is pretty obscure, as you could see there. It's just bytes, just code values. You could sit down and, if you have the programmer's reference manual for the particular processor, you could actually write out machine code directly and, flip toggle switches or whatever and put it into memory and run it. But that's pretty tedious work and not really very understandable, or easy to read when you're looking at the code. So assembly language came along fairly shortly after general programming computers were created. And assembly language is typically just a text file, and that text file is typically one instruction per line. And the instruction, as with machine language, the instruction has an opcode. That opcode is represented in the assembly language by a textual mnemonic. In the case of the 65816, that is generally speaking a 3-letter code in text that you can read as saying kind of the name of the instruction that you're trying to execute. Each instruction also has, again, an optional opcode. In this case, we have an LDA instruction followed by what is essentially a 5. In this case, it is $05. And what this is saying is that you're wanting to load the accumulator with the number 5. The $sign indicates that number is written in hexadecimal, and the number sign means that you are wanting to take the operand itself as the value to load into the accumulator. This is what's called immediate mode, and we'll get into that a little bit later when we start getting more and more into addressing modes. The second instruction there is an STA, which stands for store A, and that is given then that 3-byte hexadecimal value there. That is giving the location in memory in which to store things. Assembly language provides some things that machine language does not have. One of them is an optional label. So each instruction can be labeled. And what this label is a name that corresponds to the location that that instruction will have in memory. So this can be used as a target for when you're trying to loop through code, or you make a decision you want to branch to a different location in memory. Labels are what you use for that. And secondly, additionally, you can have an optional comment on each line. In 65816 assembly code, this is specified with a semicolon. Anything after the semicolon is a comment. The assembler will essentially ignore that. It does not get stored in machine language in any way. It's just there to help you read the code. So let's get into what is it we're going to try to do here today as an example. And again, we're going to try to do a video game of some sort. And one of the things that you might want to do, if you remember what the Foenix default screen looks like, we've got a purple border around the screen on the C256 Foenix. That may not be the color you want to have in a video game. Maybe you want the border to be green. So how do we go about changing that green color? Well, the Vicky chip has 3 single-byte registers in its system that control the color of the border. And there's a byte for red, a byte for green, and a byte for blue. And the byte value in there tells Vicky how intense that color component needs to be in the final color. If that byte is a 0, that particular component is off. You don't get any contribution from that color into the final color of the border. If it's 255, it's at its most intense setting. So if you wanted a red border, you would set the red register to 255 or something like that, and the green and blue component registers to 0. In our case, we want to have the border color be green. So we're going to want to put 255 in the green component register and zeros in the red and the blue component. And of course, you can mix and match. If you wanted yellow, for instance, you could set values for red and green that are fairly high and leave blue fairly low or at 0. Well, so how do we go about writing a value to the register? The Vicky registers are presented to the CPU as locations in memory. So really what we're going to want to do is to store a value in memory. And there are 3 store instructions that the 65816 provides. They are store A, store X, and store Y. The operand that goes with the instruction tells the processor where you want to write the value. And where the value comes from is the register that corresponds to the store instruction. STA, or store A, takes the value in the accumulator, that A register, and stores that to memory. STX stores the value in the X register, and STY stores the value in the Y register. Note that we do not have a store instruction that takes a specific immediate value and writes it. So you can't just say, if you want to write 5 to some location in memory, you can't just say store 5 to this address. That's not available in the 65816. So how do we get a value to store to a location? Well, we first have to load that value into what the A, X, or Y registers. And fortunately, there are 3 load instructions, LDA, LDX, and LDY, that are essentially parallel to their equivalent ST instructions. The operand, in this case, indicates what value we want to load into that register. And that operand can be indicating a location in memory, or, as I mentioned earlier, there's what's called an immediate mode operand, which the operand actually provides the value that you want to load into the register. So the way we can write some specific value to one of these registers in the Vicky chip is to load a value into A and then store it into memory. Now, before we actually get into that, one of the little wrinkles with the 65816 processor is that those three registers, A, X, and Y, they can have 2 different widths. The register can be 8 bits wide, meaning it can store a value from 0 to 255, or it can be 16 bits wide, meaning it can store a value from 0 to, 65535 or something like that. We need to have some way of specifying whether we're working with 8-bit values or 16-bit values. And that is actually controlled by 2 flags in the status register, M and X. M sets the width of the accumulator and of various other memory operations, and X sets the width of the X and Y registers. That nomenclature there is a little bit confusing, so that's something to watch out for a little bit. Fortunately, X really doesn't show, the X flag name doesn't really show up in 65816 assembly code. So when assembly code is talking about X, it's generally talking about the X register and not that X flag. How those flags work is that if the value is 0, then the flag is indicating that the registers associated with that flag are 16 bits wide. And if the flag is a 1, that is, if it's set, then the associated register is 8 bits wide. So we're going to want to work with 8-bit values, and we're going to work with the accumulator. So what we're going to want to do is to make sure that the accumulator is 8 bits wide, meaning we want that M flag to be set to 1. Now, there are 2 instructions that come with the 65-bit16 that let you set or clear flags in the status register. The SEP instruction takes an operand that indicates which flags you want to have set, and the RAP instruction takes an operand of a similar type that indicates which flags you want to have cleared or reset to 0. And then one final little kind of odds and ends here. we'll get this example program up and running and everything. But what happens when you're done setting the color of the border? What does your program do? Because the code's just going to keep running, and if there's no real machine language at the end of that code, then the processor can get confused and start doing all sorts of random stuff. Well, one nice thing that we're going to want to do here is to go back to the monitor, and the way on the C256 Foenix that you do that is to execute what's called the break instruction, BRK. This is what's called a software interrupt. It's kind of like a trap instruction or something like that. It is a signal to the processor that it should do something special, essentially. And typically what happens is that will go to the firmware and cause the code to go into the monitor. And that's what we do on the C256 Foenix on the stock kernel. When the BRK instruction is executed, that will stop the current program and start executing the monitor, the machine language monitor, where you can look at memory and make changes and so on. BRK is a little bit of a funny instruction in the 65816 in that it assumes that there is an operand byte after it, but for some reason, no assembler that I know of lets you put an operand byte in there, because the operand byte isn't used for anything by BRK. It's just there. So typically what I do in my assembly code is I will put an instruction immediately after it that is not meant to be executed. Because in theory, you could return from a BRK and execute the code following it. And if that code doesn't allow for that operand byte, things can be a little confusing. So that's a little bit of a caution there, and I'll get into that when we get into the actual code. All right, so let's go ahead and go into a text editor and start building up our example code. All right, so I will put up on GitHub a repository to store all the code that we're going to be looking at in the course of these tutorials. And here's the kind of the starter file that I'm going to start with right here. It doesn't have very much, but there are a couple of little things that you're going to be doing repeatedly with this code, and I've got that in here. So I've got a little bit of a preamble, and there are two features I haven't talked about yet with the assembly language that I'm going to address here. The first is this first line. Now, this is an example of an assembly directive. Assembly directives in 64 tasks start with a dot, so dot CPU. And assembly directives are essentially instructions to the assembler. Now, they do not correspond to machine language. They are not assembly language instructions. They do not generate machine language instructions. But they control the assembler and tell the assembler what it's supposed to do with the code that follows. In this case, what we're doing is we're telling the assembler that we're using a 65816 as the target processor. So it should support the instructions that are specific to the 65816. The reason that this is important is that something like 64 tasks can typically support several different processors. It can support the 6502, it can support the 65C02, it can support different flavors of those chips, and it can support the 65816. But for it to know which instructions are valid, it really needs to know which specific processor you're using. And so that's what we're doing here. The next thing is kind of a special little syntax where we're saying where are we going to put this code. So generally speaking, with 6502 or 65816 assembly code, the code is written to run from a specific location in memory. And so we need to specify what's called the origin point, and this is the syntax that we use to do that. Asterisk followed by an equal sign, and then the address of the location, the first byte of the code. There are a couple of different ways that we can do this. However, 64 Tasks supports a couple of little useful tools called segments, which are essentially blocks of memory that we're going to work with that you can specify by name. We're not going to do that here. That adds some complexity to it. And again, you can see I've got a whole bunch of comments in here kind of specifying the different blocks of our code. So let's go ahead and get started. So what is the first thing we want to do? Now I'll put in a little start label here because I like to always have that start of code labeled in some convenient manner. And really the first thing that we're going to want to do is to make sure that the accumulator is set to 8 bits in width. The reason why we want to do this is we can't guarantee on starting this code what state the processor is in terms of that M flag. So we need to make sure we've got that. And again, the M flag, if it's set to 1, means that the accumulator is going to be 8 bits wide. So we want to use the SEP instruction to set a flag in the processor. And the way the SEP instruction works is that it takes an immediate value of a single byte, and that byte value, the bits that are set in that byte, will be the bits that in the processor status register that we want to set. And for the M flag, that is 20. So we're going to want to set, what would that be? That's the bit 5 in the status register that we want to set. That's the M flag. So I'll just put a little comment there so I know what we're doing. Now, this is all very well and good, but for various reasons that we'll get into in more depth later, we need to make sure that the assembler also knows that the accumulator is 8 bits wide. And we do that with another assembly directive, in this case, AS.AS. That stands for accumulator short. So another comment there to specify that. And now we're going to want to set the actual colors in the border. So the first thing I want to do is to set the red and blue values to 0. So I want to load a value into the accumulator. Well, what I want to do is to load 0 into the accumulator. And I can do that with, again, the immediate mode operand. So load a 0. Now you'll notice I didn't use a $ in that to indicate that that's hex. 64 tasks lets you specify literal number values as either decimal or hexadecimal. If you don't have a $ on it, it will be the decimal version. And for a lot of values, I just prefer to use the decimal value. You can use hexadecimal for everything if you want, or however, it's fine. And now we're going to want to put that 0 value into the red and blue registers. So we're going to store the value in the accumulator to F0005, which I think is set blue component to 0, and 0007 set red component to 0. And now we're going to want to set the green component. And we want to set that fairly high. I'm going to say let's just load in, full on 255. Make it really bright green. And we're going to want to store that value into there we go, the green register. So after these loads and stores are done by the processor, then the border color should change to green. Then what happens? Well, we don't have anything specified. So again, what we're going to do here, and different programs might have different strategies for this. Maybe you enter into an infinite loop. Maybe you wait for the user to do something. Maybe you return back to a calling program or something like that. What we're going to do is just go back to the monitor. And just because we need some sort of value after it, we'll put another BRK instruction after that. This BRK instruction would probably never be executed, so it should be fine. You could also put in other things there, or you can just skip it altogether if you're never expecting to just kind of return from the BRK, which generally speaking on the Foenix you're not going to do anyway. But anyway, there's our code. So we're going to start off here by setting the accumulator 8 bits wide. Then we're going to set the blue and red components of the border color to 0, and meaning fully off. And then we're going to set the green component of the border to 255, which is fully on. And then we're going to exit out to the machine language monitor on the Foenix. So let's go ahead and save this, and I'm going to save it as lesson 1 ASM. Fortunately, you can't see that. There we go. So it's lesson 1 ASM. And then I'm going to want to actually assemble it using 64 tasks. Now I have set up a little batch file that will again be included with this code in the repository. And this really is just meant to be kind of a helper to set all the options that 64 tasks is looking for. And there are a fair number here, long address and flatten -b, all these things. You can read the 64 task manual to figure out what all this stuff does. What it's going to do for us in practice is it's going to generate 3 files. It's going to generate a listing file, a label file, and a hex file. The listing file is basically going to be a listing of your source code with the machine language that corresponds. The label file will be a file listing out all of the labels that you define in your code, which can be helpful for debugging purposes. And then the hex file will contain the actual machine language in a format that we can use either to send the code directly to the to the C256 Foenix, or that we can run on the emulator. So that's what it's going to do in practice. So the way we run it is down here. I just run a little batch file. And yay, no errors. That's always nice. And if I pop in here you can see, here's the listing. There's my assembly code, and here are the bytes of the corresponding machine code. So, that instruction should look kind of familiar, and this can maybe look kind of familiar. Label file, as you can see here, is pretty short. There were only 2 labels defined. This one was defined by the make file. It's not really necessary. I should clean that out before I post this. And this was the starting address that I specified earlier. And we're going to need to remember that in a moment. And then here's our hex file. This contains the actual machine language that we're going to run. All right, so let's go ahead and look at how to run this. All right, so here's the Foenix IDE and emulator. Again, there's going to be a link to its GitHub repository, and you can just go and grab it. The exe file for this and the ROM binary files you're going to need, those are all included with the project, so basically you can just clone that repository, install it on your machine, and run it directly. This is the screen of the emulated C256 Foenix, and this is kind of a little control panel that shows you what's executing, shows you the different registers on the processor, and all that sort of stuff. This is also where you can start it and stop it. So I'll go ahead and click the run and let it boot up. All right. And now what I want to do, I'll go ahead and pause the processor. I want to go and load the hex file that we created earlier. And there are 2 ways of doing it. For this kind of thing, I do load hex file without zeroing. Zeroing means that it clears out all of the RAM before it loads the hex file. For these kinds of programs, you don't want to be getting rid of the kernel, so which is what would happen otherwise. So we want to just go ahead and do load hex file without zeroing. And here's the file we just created. So go ahead and load that, and then I'll start running the computer again. And then probably the easiest way to do this is, let's just jump to it from here. We can just put the address that we want to start executing, 010000. That was the start address of our original code, and I can just click jump. Now notice that I've got colon here. Kind of the convention with the C256 is that we put a colon there between the third and second most significant bytes of an address, just to make it a little bit more legible. The colon really doesn't mean anything, it's just kind of a separator. Anyway, we put in 010000 and click jump. And there we go. We have a green border, as you can see, and we've popped out into the monitor. And that's pretty much it for this demo. So this was meant to be pretty simple because we did have to go through a lot with machine language and assembly language. I'm hopeful that when I get around to the additional tutorials that are going to follow, that we'll have more actual demonstrations, more actual example codes to work through as we go through the features, and less general babbling. Anyway, I hope you found this useful, and stay tuned to this channel, and I will be producing more videos along the series. And if you have any questions or comments, any suggestions for improving this stuff, do put it in the comment section below. I do value your feedback. Thank you for watching.